Hi, this is Mrs. Bowen with the University of West Florida, and we're picking up on our lecture where we left off on spring break. Wanted to reintroduce very quickly the concept that we started on spring break, which was finding an x value for the for the normal distribution. And for a normal distribution with the known values of mu and sigma, and for a given area under the curve between the mean and the x value is calculated as follows. It's right here is our formula. And if you pull up your formula sheet over here on page 2 of your formula sheet, you will see this same formula right here. It's called the raw score. Now you can go ahead and remember that it's there and remember to use it. However, if you don't have that handy, most of my students will always have our z formula memorized, which is that z is equal to x minus mu divided by sigma. And all we did is solve for the x in this situation. So it was x equals. So we're just going to do simple algebra. We're going to multiply both sides by sigma, which will then give us sigma z is equal to x minus mu. We're solving for x, so we're going to add mu to both sides. And we end up then with mu plus sigma z is equal to x, or x is equal to mu plus sigma z. And remember, with multiplication, order is not important, so these two are the exact same. So when would we need this? Let's look at this example right here. It says, recall our earlier example. It is known that the life of a calculator manufactured by Intel Corporation has a normal distribution, that's very important, with mean of 54 months and standard deviation of 8 months. What should be the warranty period to replace a malfunctioning calculator if the company does not want to replace more than 1% of all the calculators sold? So when we look at this, reviewing what we had before, is the company does not want to replace that many. At most, they want to replace 1%. So that means we're going to be looking at the left tail, and we're going to have an area over here of 0.01. So the calculators would be replaced. Okay, those are the ones that start to malfunction, during the warranty period, and we're trying to figure out what the warranty period should be. The company's objective is to replace at most 1% of the calculators sold. So the shaded area right here, okay, gives the proportion of calculators that are going to be replaced. And so what we need to do is we need to find out what value of x corresponds with this shaded area. So we drew our first picture right here. We put our mean of 54 months in the very center. We did not have a 35 right there. Then we drew a mirror image of that, our sister graph, which is the standard normal distribution. And we had to find out what z value corresponds with 0.01 being right in here. And we pulled up our z tables, and we found out that it is a negative 2.32. So when we come in here, we look for 0.01, and 0.01 is going to be right about here. So this is about as close to 0.01 as we can get without being there. And so it's negative 2.33. So negative 2.33. Or negative 2.32 on the graph. Let me go back and double check that one. In class I did 2.3, but I think I should have done 3.3 is what I should have done, because that is the closer value. If you look at that, negative 2.33 would have been a better choice in class. And so the value right here should be negative 2.33. So we're going to say then that x is going to be equal to mu, which was 54 months, plus sigma. Sigma is 8 months. So 8 months times our z, which was negative 2.33, looking at that on the correction there. And we'll pull up a calculator here real quick. And clear that out. And so we're going to say that x is equal to 54 plus 8 times negative 2.33. And we hit enter and we get 35.36. So therefore x is equal to 35.36. So the warranty period basically should be about 36 months. If they offered a 3-year warranty on the calculators, they would replace approximately, at most, 1% of the calculators. And a 3-year warranty would be reasonable and something that most people would appreciate. So that's how we solved that one and why we solved that, because we did not have this value, but we knew that the area under the curve was 0.01. The z-value that corresponded to that should be negative 2.33, and we simply used our formula here then to solve for x. Another very similar problem. It says almost all high school students who intend to go to college take the SAT. In recent years, the mean SAT score in verbal and mathematics has been around 900. So the mean has been around 900. Mary is planning to take this test in her senior year. Suppose the SAT scores of all students who take this test with Mary will have the normal distribution with a mean of 904 and a standard deviation of 153. What should her score be on the test so that only 10% of the examinees score higher than she does? So we need to go ahead and draw a picture of what we're asking here and what it looks like. So we're going to go ahead and we're going to grab some ink here and we're going to draw a picture of the initial situation. And we know that in the center is our mean, and the mean is 904. So we're going to put 904. And we're saying that we want to find a value of x so that 10% of the people score higher than Mary, but not more, okay? So we're going to put x. We don't know what that value is. And we can draw another picture just like it right below it. And it looks just like this. And we're going to say, well, we know that the mean is 0 for the standard normal, and we don't know yet what this z-value is, but we can find it out, okay? And we know that under here, we're going to have 0.10. If we have 0.10 to the right of the pink line, that means that we know that we have 0.90 to the left, because 0.90 plus 0.1 have to add up to 1.0 underneath the curve, okay? And so we're going to go ahead and just highlight this area over here so we know the area that we're interested in. We need to find the z-value that corresponds to this, so we're going to pull up our tables. Remember that our UWF tables give us the left tail, and so we're saying that the left tail, this whole thing over here, must be 0.9, and that's the area under the curve, which means I'm looking in this part of the graph, okay? So we're going to come in here and we're going to find 0.9 or a value as close to 0.9 that we can get. So I'm looking in here and I'm looking and I'm seeing some values, and right here, okay, I go from 0.89 to 0.9. So which one of these two values is the closest? It's going to be this one right here, okay? So the 0.8997 is going to be the z-value that is the closest z-value that we can get from the tables, where that we have 90% of the area under the curve is to the left of this value. And so that z-value is 1.2, and then it should be 8. So we're going to scroll right on up, and 0.8, okay? So 1.28, okay, is our z-value, and it's a positive number. So this is 1.28. So what do I know? I know what my mean is. I know what my standard deviation is. We know that mu is equal to 904. We know that sigma is equal to 153, and we know that z is equal to 100 or 1.28. Okay, so really what I have is I have 1.28 is equal to x, that's what we're solving for, minus our mean divided by our standard deviation. Okay, let me switch colors here. There we go, that's better. So this is really what we have. We can solve this and by multiplying both sides by 153 and then adding the 900. So we end up with x is equal to 900 plus 153 times 1.28. We will grab our calculator and turn it on, clear it out, and now I have, whoops, right here, this should be 904. And this one right here should be 904. There we go. I had 900 from this part right here stuck in my mind. So here we go. So we'll grab our calculator and we will go 904 plus 153 times 1.28, because that's how many standard deviations away the x value is, and we find out that that is 1099.84. So x is going to equal to 1099.84, or I would say x is going to be equal to 1100. So 1100. Okay, is approximately what x would be equal to. So we'll put, there we go. Alrighty, so there you go. That is that problem. So x right here will equal 1100. We have another problem here. I encourage you to go ahead if you want and to pause your video right now and see if you can solve this one on your own, and then push play just to see how you do. Okay, so hopefully I gave you enough time to push pause, and now I'm going to solve this and hopefully you can compare your answer. If you just want to fast forward to the answer to see if you got it right, go ahead and do that. That's the beauty of the internet and video lectures. Okay, so here we go. IQ scores for a group of 6th graders are normally distributed, important, with a mean of 100 and a standard deviation of 12. What is the probability that one singular randomly selected student will have an IQ score between 90 and 110? So we're going to write this down. We're going to say, what's the probability that 90 is less than X? That's the score for the individual student that we selected, which is also less than 110. That's how we mathematically write that. Let's draw a picture that represents the problem we're being asked to solve. In the very center, we're going to put the mean, and we said that the mean was 100. On the same axes here, we're going to put 90, and we're going to put 110. And we're saying, what is the probability that we randomly select one student, just one, and their score on the IQ is between the value of 90 and 110. So this is a picture that represents the question being asked. In order to solve this, we need to standardize the 90 and the 110. We need to standardize both of those values. And in order to do that, we're going to draw another picture. That looks really sad. Let me do a better picture here. And we're going to put our mean in the center. Remember, when we standardize, our mean is 0. And then I'm going to label my negative z and my positive z. But I don't know what those values are because I have to do math on these numbers to solve. So the first number I'm going to standardize is the 90. So z is equal to 90. Subtract mu, which is 100. So remember, mu is equal to 100. Sigma is equal to 12. Right there, okay? Divide it by 12. And we're going to put this in our calculator. And we should get a very quick answer. So we're going to turn on our calculator, and we get 90 minus 100. Hit enter, and then divide by 12. I'm going to make sure you pay attention to your order of operations. So it's negative 0.83. So this is negative 0.83. That's what my z value is on the left-hand side. Whoops. On the left-hand side here, when I standardize the 90. Now the next thing I need to do is I need to standardize my 110. So I need to find out how many standard deviations away from the mean is the value 110. That's what the z-score, z-value is giving me. So this is going to be equal to 110 minus 100 divided by 12. And we can bring up the calculator again, and we'll hit clear. And I'm going to use parentheses this time, so I'm going to go 110 minus 100 divided by 12 is equal to, well, okay, 0.833. So positive 0.83, 0.83. And the area under the curve that we're looking for, okay. Alrighty, so let's look at an equivalent. We are asked to solve the probability that a randomly selected student has a score between 90 and 110. That's the exact same thing as saying, I want to find the probability that the student is between negative 0.83 standard deviations below the mean to 0.83 standard deviations above the mean. Okay, that's the exact same question. So when we look at this right here, I'm going to bring this down. I'm going to say this is the probability that negative 0.83 is less than z, which is less than 0.83. That is equal to the probability that z is less than 0.83 minus the probability that z is less than negative 0.83. So what that's doing is it's saying I'm going to take calculate the probability that z is less than 0.83, and then I'm going to subtract off the probability that z is less than negative 0.83. And so if I calculate all of this and then I subtract off this part in here, what do I have left? The green part, which is the answer. So let's find out what the probability that z is less than 0.83. 0.83 is going to be 0.83 right here. So this is 0.7967. So 7967. So 7967 subtract, and now the negative 0.83. So we're going to come up to the negative 0.80123. So it's 2033 right here, 0.2033. So 2033 subtract 2033. We're going to put that in our calculator. And let's see here. We'll just do this one real quick. So 7 minus 3 is 4. 6 minus 3 is 3. 9 minus 0 is 9. And then 7 minus 2 is 5. And I didn't quite give enough room there. 5. So that's 0.5934, giving us a little bit more room there. So how'd you do? I hope that you did really, really well. And if you are listening, and if you did this problem on your own prior to and you got it correct, send me the code word hot dog. Just send me an email or a text. Remember, my phone number is 850-376-4644. 4307. Make sure you include your name so I know who's sending me the message, and just you don't have to say anything else, and just hot dog, and then I'll know that you got it right and you did it on your own. Here is another problem. Same situation. Go ahead and push pause if you want to and see if you can solve it on your own, and then in a moment I'll solve it for you, and you'll see how you did. Okay, here we go. So the Gear Tire Company has just developed a new steel belted radial tire that will be sold through the national chain of discount stores. From road tests with the tires, it is found that the tire mileage is normally distributed with a mean tire mileage of 36,500 miles and a standard deviation of 5,000 miles. What is the probability that the tire will last at least 30,000 miles? That at least is very important. So we're saying I'm going to randomly select a tire, so it's a single tire, and I'm wanting to know what's the probability that that tire will last at least 30,000 miles. And so that's a picture, or that's a written mathematical statement of the question being asked. So let's draw a picture that represents the question being asked. In the center, we're going to put mu, which is 36,500 miles. And then it says, I want to know the probability that X lasts greater than 30,000. So I'm going to come over here, I'm going to write 30,000. And we're going to grab a highlighter, and we're going to say we're looking for this area under the curve over here. And that's what we're looking for. Now the next thing I want to do, remember, we always want to take and write another picture that shows the standard normal and is our mirror image sister picture. Okay, the standard normal. So we know that the mean is 0. And what we don't know yet is what is the z value that corresponds with this, so that we can say that 30,000 is how many standard deviations away from the mean. That's what our z is. That's what we're calculating. How many standard deviations in this case below the mean is 30,000. That's what we're being asked to find out. And we'll go ahead and shade it the same way because we want our pictures to look the same. And we just need to go ahead and find out then what our z value is. So we're going to say z is going to be equal to, remember, it's x minus mu divided by sigma. So we have one individual tire. We don't have a group of tires. We have one tire. We're saying what's the probability that one randomly selected tire lasts at least 30,000 miles. So it's going to be 30,000 because that's what we're going to let the x equal, minus our mu, which is 36,500. We're going to divide through by sigma, which is 5,000. So let me go ahead and write that up here. Mu is equal to 36,500. And then sigma was equal to 5,000. It helps if you write that down at the very beginning. So divide it by 5,000. And we're going to grab our calculator and we're going to throw this in. It's going to be 30,000. Let me put up parentheses there. So 30,000. 1, 2, 3, 4. Minus 36,500. We're going to close that parentheses, and then we're going to divide through by 500. Very important that you open and close parentheses accordingly. And so our z value is negative 1.3. So negative 1.3. So negative 1.30. And so in that case, that tells me that this is the exact same thing as saying what's the probability that z is greater than negative 1.30. That's really what's being asked. And I need to know how much area is highlighted in blue, and that's to the right of this negative 1.30. Well, remember, our, well, let me not pick that color. Let me pick this color. Our UWF tables give us this part right in here when we look up negative 1.3. So let's grab our tables. look up negative 1.3, so negative 1.30. So here's our value, the area under the curve to the left of negative 1.30 as a z-score. And we find out that that is 0.0968. So 968. So this right here is 0.0968. And I can say the probability that z is greater than negative 1.30 is going to be equal to 1 minus 0.968, because my memory sometimes fails me. I'm going to go back and just double check to make sure I have that right. 1.30968, yep. And we're going to punch that on our calculator, and we're going to find out that 1 minus 0.0968 is equal to 0.9032. So right over here is 0.9032. Same thing right up here, 0.9032. And it's okay if you go ahead and write this down here, this 0.0968, because it's good for you to have the whole area represented under the curve and it all adding up to 1. It helps you understand exactly what's going on and why we're doing what we're doing. Okay, so the probability that we randomly select a tire, that's one single tire, out of a group of however many tires, and that we test it, and it lasts at least 30,000 miles. The probability of that happening on this particular tire that's going to be sold at a discount store is 0.9032, or we could say that 90.32% of the tires will last at least 30,000 miles. Okay, another one, if you all want to pause this for just a second and see if you can solve it, then you'll see how you're doing, and if you get it right, just fast forward on through. Okay, so here we go. We say test scores for a college midterm exam are normally distributed with a mean of 72 and a standard deviation of 13. Suppose the professor wishes to assign a grade of an A to the top 15% of the students obtaining the highest scores in the class. What is the cutoff score for the A? So that's what we're looking for. So what we're saying here, let's go ahead and we'll say mu is equal to 72 and standard deviation is equal to 13. So we'll draw a picture, and our picture looks like this. We're saying that we have, whoops, my computer's getting hot. Then in the very center, our mu is 72. And I want to find some value. I don't know what the value is, but we're going to call it x, where that only the top 15% of the people make an A. So we have 15% in here, and then 1 minus 0.15, right? It's going to be 0.85. So we're going to have 0.85 over here. And I need to go ahead and draw my mirror image of my sister graph. My standard normal graph is my mirror image. And I'm going to find my z value, okay, which I can find. I can't find x right away, but I know what my z value is going to be. If I have 0.15 here, that means I have 0.85 over here. My UWF tables give me this area right in here at 0.85. So I can pull up my UWF tables and I can find 0.85 underneath the curve. We know it's going to be a positive value because 0.85 is greater than 0.5. So we're going to come in here, we're going to say 0.85 is going to be right about here. So 0.01 or 0.1234. So 1.01 right here is going to be our z value that corresponds with approximately 85% of the area to the left of it. So our z value is going to be equal to, oops, it's going to be equal to 1.04. Okay, so again, I look up the area under the curve at 0.85. I found the value closest to 0.85 in the chart. It wasn't exactly 0.85, but it was as close to 0.85 as I could get. And the z value that corresponded to that was 1.04. And I'm being asked to solve for x. And I happen to know that x is equal to mu times mu plus sigma times z. So mu is 72 plus sigma, which was 13, times our z of 1.04, and therefore x is equal, if we punch that in our calculator, we're going to find that it's 85.52. 85.52. So x right here is equal to 85.52. So z would be just over one standard, or x rather, is going to be just over one standard deviation above the mean, and the value is 85.52. So that says anybody who either made an 85 or an 86, typically the professor would have chosen 85. So it's anybody who made over an 85 on this midterm exam would have made an A. So that's how we would properly interpret that. So to earn an A, on the midterm, the student let's try that again. The student would have to make at least, that is at least, I promise you that spells at least an 85. Okay, so how'd you do? Hopefully you got that one right. If you did, text or email me the code word watermelon. Okay, and yes, I'm paying attention to who's sending me the code words. So don't be bashful and say, this is kind of weird and awkward. I'm looking for it, okay? So hopefully I'll have 90 students, or I think at this point we have 88 students left in the class, sending me these code words. Let's go on to the next problem. Okay, now we're starting a brand new concept. So what we're going to be learning about is slightly different than what we've been working on. What we've been working on is determining the probability that we randomly select a single item or a single individual and finding out that that element has a particular value. Okay? What we're going to be switching to now is, instead of saying that I'm going to be looking at the probability of a single event of selecting one person, and let's say when we go back to our classroom, and I always talk about, the probability of selecting somebody in our classroom, and let's say that they are at least 40 or 30 years old, okay? Now, we don't have very many students in our classroom that are over 30 years of age. We do have some, but not a lot. So the probability of me randomly selecting one student and having their age be over 30 is, it exists, but it's not even 50%, okay? It's probably not even 20%. It's probably more around 15%. However, what if I said, out of the 90 students that sit in our classroom, I want to randomly select 20 students. So my sample size is 20. I want to randomly select 20 students. And I'm telling you that the classroom is normally distributed on their age. And I say, well, what's the probability that I select 20 students randomly and the average age of those 20 students is greater than 30? Now that's a whole different ballpark, isn't it? Now what we've got is, instead of saying what's the probability of me randomly selecting one individual out of the 90 students in the classroom and having that one individual be over 30, I'm saying I'm going to take in a random sample of 20 students, and I'm going to average together the age of those 20 students, and I want to know the probability that the average is over 30. That's not probably going to happen, is it? I don't even know that we have enough, if it could actually happen with our current data set of our students in our classroom. So the probability of that event happening is extremely small. Well, that's what we're going to be talking about right now, is we're going to be talking about randomly selecting a sample and determining what the probability of the mean being a certain value as opposed to an individual. Okay, so that's where we're headed to right now. So it says the proper population distribution is the probability distribution derived from the information of all elements of a population. Okay, so the population distribution is from all elements of a population. So here's my definition in a nice little pretty box where it says the population distribution. The population distribution is the probability distribution of the population data. So all it's saying is let's make a frequency distribution. Let's put a graph together that represents the frequency, and we're going to call that a population distribution, okay, as opposed to a sample distribution. So let's look at this a little bit closer about what we're actually talking about. Suppose there are only 5 students in an advanced statistics class, and the midterm scores of these 5 students are as follows. So we only have 5 students, so the whole class only has 5, so that gives me a capital N equals 5. And my midterm scores are 70, 78, 80, 80, and 95. Okay, so we're going to let X denote the score of the students. Using the single value class, as there are only 5 data values, we can write the frequency distribution as follows. So what values of X can it assume? Well, we have a 70, a 78, an 80, and a 95. Remember right here, my 80 occurred twice, so now we're going to do the frequency. 70 occurred once, 78 occurred once, 80 occurred twice, so frequency is 2, F for frequency, and then 95 occurred once. So my N is equal to 5. The probability of each one of these events happening, what's the probability of getting a 70? Well, I have 5 total. One time did it occur, so it's 1/5. What's the probability of X equaling 78? Of a student scoring a 78, I only had that occur one time out of 5, so it's 1/5. What's the probability that a student got an 80? Well, we had 2 students get an 80, so the probability of scoring an 80 is 2/5. What's the probability of scoring a 95? We only had 1 student, so the probability of scoring a 95 is only 1/5. So quality control check. The frequencies should sum to our population size, which is 5, and our probabilities associated with each event occurring should sum to the number 1, and it does. So that's very important that you always make sure that you do a quality control check right there and there. Okay, so let's move on just a moment. So it says the values of the mean and the standard deviation calculated for this, okay, probability distribution give the values of the population parameters of mu and sigma, because this is 100% of the students in the class. 100% of the student, capital N, is equal to 5. So I can actually calculate mu. Mu is equal to 80.6, and I can actually calculate sigma. Remember, sigma and mu are Greek, therefore they represent parameters, which represent the population parameters, okay? And so that is 8.09. The value of the population parameter is always constant. It doesn't change because it represents the entire population. It's every single observation that can possibly occur, and it's the mean of all those possible values being calculated, trimming off all the values, okay? So it doesn't change. We're not ever changing the sample size, or not the sample size, the size of the population, because it is every single element that's possible. And therefore, if we have the population data set, we can only have one value of the mean, and the same concerning the sample standard deviation, or the population standard deviation. However, we cannot say the same thing about the sample mean, okay? The sample mean can be different, because if this is my entire population right here, I could say, well, let's let a sample size be equal to 4. Well, if I was going to calculate the mean, I could have chosen the first 4 data values that occurred, okay, which would actually be these right here to calculate a mean, would that give me the exact same sample mean, x bar, as if I used those? No, it wouldn't. And what if I used this one, and these two? Okay, that would give me a different one also. So when you change the sample mean because of the values that are selected, your x bar is going to change based on your sample, but your population parameter is fixed. We would expect different samples of the same size drawn from the same population to yield different values of the sample mean. The values of the sample mean for any one sample will depend on the actual elements included in that sample, who got chosen to be in the sample. Consequently, the sample mean x bar is a random variable, okay? It changes, it's a variable, it varies based on the elements that were selected to be in that sample. Therefore, like other random samples, the sample mean x bar possesses a probability distribution which is more commonly called a sampling distribution of x. In other words, other sample statistics such as the median, mode, and standard deviation also possess sampling distributions. Okay, so the sampling distribution of x is the probability distribution of x bar is called the sampling distribution. It lists the various values that x bar can assume and the probability of each value of x bar. So basically what we're saying, not basically, what we are saying is the sampling distribution of x lists every single possible combination of a fixed sample size. Okay, that's key. Of a fixed sample size. You're not varying your sample size, but a fixed sample size, every single possible outcome of x bar is going to be listed, and we're going to make a frequency distribution, and that frequency distribution has a special name. It's called the sampling distribution of x bar. So this is nothing more than a frequency distribution of all the possible values that x bar can assume, the means could assume, based on a fixed sample size. So explaining this again, reconsider the population midterm scores of the 5 students. Consider all possible samples of 3 scores each that can be selected without replacement from that population. So I have 5 students. If I'm going to choose 3 scores each, that gives me a sample size or total possible outcomes of 10. Okay, 10 different combinations. So we can let event A be that the student scored a 70. We can let event B be that they had a 78. We can let event C be that they made an 80. We can let event D be that they had an 80. And we can let event E be that they made a 95. Okay, so that represents all the different possible scores. I'm selecting 3 of them, so I have 10 different ways that I can select 3. Order is not important. So I could get A, B, C, and if I had A, B, C, that would mean I would have a 70, 78, and 80. A 70, 78, and 80. Or I could say I have A, B, D. So A, 70, B, 78, D, 80. Or I could say I could have the combination of A, B, E. So A, 70, B, 78, E, 95. Okay? And so all of these right here are just all the different combinations of how I can list choosing 3 out of 5 students. Okay, that's all this is. And then I wrote down the associated score with each event. Then I took and I calculated the average. So if I average these together, I get 76. If I average this together, I get 76. If I average these scores together, I get 81. If I average these scores together, I get 76.67. And I did that for every single possible combination. I listed the x bar. Now, what I have is I can look at what are all the possible outcomes listed here for x bar, and I can make a frequency distribution from that information. Okay, so that's a frequency distribution, but because it has to do with x bar, we're going to call it instead a sampling distribution of x bar, but it's just a frequency distribution of the x bar values. So this chart right here is recopied on the next page. So just hang tight. Here we go. It's right here. Okay, so here's that exact same information. Okay, here's all the possible values of X bar, and I listed them right here. Okay, this is all of the different possibilities. So I have a 76, okay, 76 right here and right here. So the frequency is 2. I have a 76.7, and I only have one of those, and that is right there. So frequency is 1. I have a 79.3. That only occurs one time, and so it has a frequency of 1. I have an 81, and an 81 occurs one time right there, and so I listed the frequency as once. Another possible mean that I could have calculated for a sample of 3 students with their grades on the midterm was they could have had a sample mean of 81.67. Well, 81.67 occurs twice, so I have a frequency of 2. Another sample mean that could have occurred is an 84.33. Again, that happens twice, so the frequency is 2. And then I have the last one here of the 10 options is an 85. It occurs one time. Now I can sum all of this together, and we will see that it adds to the frequency of 10, which makes sense because I had 10 different ways that I could choose 3 students from a classroom that had 5 students in it. Okay, 10 different combinations. And now what's the probability of each event happening? The probability of each event happening, it's going to be the frequency divided by the total number of possible outcomes. So 76 occurred twice, so the probability of the average of me randomly selecting 3 students and finding out that their average score was a 76, the probability of that event happening is 0.2 or 0.2. So 20% of the time I could randomly select 3 students and find out that their average scores was 76. What if I put everybody's score back in a bag and I pulled out 3 new scores and I found out that the average score was 76.67? Well, what's the probability of that happening? Well, it can only happen with one particular combination, so the probability of that event happening is 0.1. And we can go all the way through, okay? And it's going to be the frequency divided by the total for all of these. And that's how I got the probability distribution, which is right here, okay? So, if we select just one sample of 3 scores from the population of 5 scores, we may draw any one of the 10 possible samples above. Hence, the sample mean X bar can assume any of the values listed above, which would be these values right here. So the mean of the sampling distribution of X, we're making a frequency distribution, okay? I can make a frequency distribution out of this information right here, and that would be called the sampling distribution, okay? So the mean of the sampling distribution of X bar is equal to the mean of the population, okay? So the mean of the sampling distribution, if I went through here and I calculated, right here, and I calculated the average value right here, that's the exact same thing as what's the mean for the entire population. I'm going to change my color up here. Let me grab a different color. There we go. Okay, so let me highlight that better. There we go. Alrighty, so if I calculated the actual X bar, in other words, if I took all of these values, added them up together, divided by 10, that would be mu. Mu also happens to equal the average distribution about X bar, meaning I can then calculate it off of these values and I will get one and the same answer. Okay, the sample standard deviation of X bar is equal to the standard deviation of the raw data divided by the square root of the sample size. So it would be whatever sigma is for the raw data divided by the square root of the sample size. The sample size in this case, what we've been talking about, is 3. So it'd be divided by the square root of 3. Okay, where sigma is the standard deviation of the population and n is the sample size. So here we're going to work on terminology and making sure you understand the mathematical correlation with the appropriate terminology. Okay, that's what we're going to be working on. So it says the mean wage per hour for all is important, that's the population then, 5,000 employees working at a large company is $13.50 an hour. And the standard deviation is $2.95. So I wrote that information down here. Here's my mean. Here's my standard deviation. Here's my mean. And here's my, not sample size, but my population size, because it's all the employees of a large corporation. It says let X bar be the mean wage per hour for a random sample of a certain employee selected from the company. Find the mean and the standard deviation, X bar, for the sample of the following sample sizes. So case number 1, n is equal to 30. So the first thing it said is, what is the mean? So we want to make sure that you remember that, and this is the mean of the sample distribution. So it's mu X bar. We're saying that this is the mean of X bar by definition that we just talked about. That is equal to mu. And we were given that mu is equal to $13.50. That easy. You've got to know, though, that mu sub X bar is equal to mu. Now, the next part is what's the standard deviation for the sample, okay, of X bar. That's going to be written just like this. So it's sigma sub X bar, and that formula is equal to sigma divided by the square root of n. What is sigma? It's $2.90 divided by the square root of n. N in this case is 30. So we're going to punch this in our calculator, and we're going to find out that this is 0.529. So it's 0.529. Okay, so make sure you take a moment and throw that in your calculator so that you know that we're on the same page with that. The next one, it says n is equal to 75. It wants to know what is mu of X bar. What is the mean of the sampling distribution of X bar? That's the same thing as the population mean, which is still $13.50. That does not change. Sigma changes about X bar because the sample size changed. It's still going to be $2.90 divided by the square root of our sample size, which is 75. And we're going to throw that in our calculator, and we're going to find out that that is equal to 0.335. Okay? Is there one more? There's one more. Push pause. You saw this on your own, then push play to see if you got it correct. Okay, same thing. So we have mu sub X bar is equal to mu. It hasn't changed. It is $13.50. Now I need the standard deviation about the mean. That is equal to the standard deviation divided by the square root of n. So this is equal to $2.90 divided by the square root of n, which is 200. And we're going to throw that into our calculator, and we're going to find out that this is equal to 0.205. And I want to take a moment real quick and look at our formula sheet and see where this information is on our formula sheet. It's right here. They don't have it in that same notation where they don't have that this is sigma sub n X bar, but if you want to write this in on your formula sheet, you may do so. Okay, you may write on here that this is equal to sigma sub X bar is equal to sigma divided by the square root of n. Let's see if it's over here. It might be on the second page somewhere. Nope, Okay, here we go. Now this brings us to the central limit theorem. And the central limit theorem is so very important when it comes to statistics. You need to make sure that when you use the central limit theorem that your assumptions are valid. Okay, as long as your assumptions are valid, you can proceed forward. But it's very important that you know that what assumptions need to be made and that they are actually valid for the situation that you're employing them. Okay, so the central limit theorem says the following. According to the central limit theorem, for a large sample size, the sampling distribution of the sample mean x bar is approximately normal in respective to the shape of the population distribution. So it doesn't matter if the data comes from a uniform distribution, if it's skewed to the right, skewed to the left, if it's bimodal, the distribution shape doesn't matter as long as we get a large enough sample. Then the x bars, the distribution of the x bars, because n is sufficiently large, the distribution of the x bars will assume a normal distribution. Very, very important, very powerful. The mean and the standard deviation of the sampling distribution are, again, mu is sub x bar is equal to mu, and then sigma sub x bar is equal to sigma divided by the square root of n. The sample size is usually considered to be large if n is greater or equal to 30. That is a general rule. Sometimes in real life applications, we need a larger size n. But for this class and for your applications right now, we're going to say anything 30 or larger is sufficient to assume normality and invoking the central limit theorem when it comes to looking at the distribution of x bar. Okay, just remember in real life, it may be that you need something larger than 30. Due to the central limit theorem, we can say that if we take all possible samples of the same size from the population and calculate the mean for each of these samples, then about 68.26% of the sample means will be within one standard deviation of the mean. So x bar plus or minus one standard deviation, approximately 68.26 of the data value, or the not data values, but the x bars will fall between 1 and 2 standard, or plus and minus 1 standard deviation. If we take all possible values, again, large size of the population, and calculate the mean for each of these samples, then about 95.44% of the sample means will be within 2 standard deviations of the population mean. Very powerful, very important. Last one. If we take, again, all the possible combinations, again, of a large sample size, and we calculate the mean of these samples, and again, the sample size must be large, at least 30 or larger, then we know that 99.74% of the sample means will be within 3 standard deviations plus or minus of the sample mean. That is very, very important. Very strong theorem, very important foundation for statistics. Okay, now we've talked about the sampling distribution of x bar when x bar is large. We can calculate a z for x bar, and our formula is as follows. It is z is equal to x bar minus mu divided by the sigma about x bar. So that is the same thing as then saying x bar minus mu divided by sigma divided by the square root of n. Okay, because remember that sigma sub x bar is equal to sigma divided by the square root of n. So we just substitute that in. So it says assume the weight of all the packages of a certain brand of cookies are normally distributed with the mean, let me grab my highlighter here, with a mean of 32 ounces, and again, we're normally distributed, and a standard deviation of 0.3 ounces. Find the probability that the mean weight, so we're taking an average, the average weight of a random sample of 20 packages, so we're not looking at just one package of cookies, we're looking at a sample of 20 packages of cookies, and we're calculating the mean weight of those 20 packages. And we're saying what's the probability that the mean weight will be between 31.8 and 31.9 ounces. So let's look at what we've got going on here. I want to erase this part real quick. Okay, so it says we have the mean weights are normally distributed. We have the mean ounces, mu, is equal to 32 ounces. The standard deviation is equal to 0.3 ounces. And we're being asked to find the probability that the mean weight of a random sample of n is equal to 20 will be between 31.8 and 31.9. So I'm saying, what's the probability that I'm randomly selecting 20 packages? I'm going to calculate the average weight of those 20 packages. And I want to know the probability that that average weight is going to be between 31.8, it's less than x bar, not just x, but x bar, which is less than 31.9. That is the question being asked. Let's draw our picture that represents this. So our picture looks like this. Come in here, and we have our mean in the center, which is 32. Randomly selecting 20 packages, and we wanted the probability that the average weight of those 20 packages is between these two values right here. Right here. Okay, so what I need to do is I need to standardize this value and standardize this value. I need to find out how many standard deviations away from the true population parameter of mu those average weights are, and then I can determine the probability of this event occurring. So we're going to draw our standard normal curve that represents this exact same situation. And we're going to have a z here and a z here. I don't know what those values are. I have to calculate those values. So I know that z is going to be equal to 31.8. It's this value right here. Its x bar is going to be equal to this minus my mean, which is 32. And we're going to divide this through by our sigma, 0.3, divided by the square root of 20. Okay, and when we put this on our calculator, I want you to pay attention to how I do this with parentheses. It's very important that we put parentheses around the numerator and then again around the denominator. So we're going to open up with a set of parentheses, and we're going to go 31.8, and we're going to subtract off 32, close parentheses, divide, parentheses, 0.3 divided by the square root. Where's my square root? Is it right there? Yep. 20. Now notice I have to take and hit this button right here. So because right now I'm currently underneath the radical, so I have to hit this button right here to move out from underneath the radical. And now I close my parentheses, and now I hit enter. And so my z value is going to be negative 2.98. So negative 2.98. So negative 2.98. So negative 2.98 is the first one. I still need to find the z value for this one right here. So we're just going to scroll up just a little bit, and I'm going to say z is going to be equal to my other x bar value, which is 31.9 minus 32 divided by 0.3 divided by the square root of 20. And again, we're going to throw this in the calculator. And if you did a good job and you know exactly, let's see, I should be able to do something like this. And I think, do I hit enter? Yeah, and that brings it back up again. And then I can just come back over here to the left, and I can change this one value right here. It's 31.8 to 31.9, and I can make that a 9. And now I can hit enter. And it will give me the other value, which is negative 1.49. So negative 1.49. Negative 1.49. So negative 1.49. So the reality is, when I look at this, this right here is the exact same thing as what's the probability that negative 2.98 is less than z, which is less than negative 1.49. 1.49. Those are two equivalent statements. I have my pictures, they agree, my statements agree. Now I need to calculate this. So using my UWF tables, I'm going to say that this statement right here is equal to the probability that z is less than negative 1.49. That's going to give me all of this area here. And then I'm going to subtract off the probability that z is less than negative 2.98. So I'm going to subtract off this area here, and then what would I have left? This area right in here. So this is going to be equal to, the first one I need to find out is negative 1.49. So we're going to come to our tables, bring this up, go to the negative. So negative 1.4 and 9 is going to be all the way over. So it's 681. So 0.0681 subtract, that's for this value. Now we're going to go look at 298, 2.98. So 2.9 and then 8. It's going to be right here. So it's 0.0014. So I just have to remember a 14 as I get over here. So 0.0014. And throw this in our calculator. And I'm going to find out that 0.0681 minus 0.0014 is equal to 0.0667. So what is the probability that I'm going to randomly select 20 packages of cookies and have the average weight of those 20 packages of cookies be between 31.8 ounces and 31.9 ounces. The probability of that happening is 0.0667, okay? Or 6.67% of the time that would happen. Not very likely, okay? It's not going to happen very often. Okay, according to the National Association of Realtors, the mean price of houses in the Northeast region of the United States was $165,100 in 1992. Suppose the current price of all houses in the Northeast region have a probability distribution that is skewed to the right with a mean of 165,100 and a standard deviation of 29,500. Let X bar be the mean price of a sample of 400 houses selected from this region. Please note that the sample size of 400 is well over 30, and that will take and negate the skewness that we talked about right here, and so that we can assume that X bar will be normally distributed. That's very important. What is the probability that the mean price obtained from the sample will be within $3,000 of the population mean? Will be equal to $165,100. Our standard deviation is equal to $29,500. Okay, and our sample size is going to be 400. And it says, what's the probability that the mean price obtained will be within $3,000? So this is saying the probability that, what's $3,000 off of this? That would be $162,100 will be less than X bar, which will be less than, now we're going to add 3,000 because it says within 3,000 either direction, okay? So adding 3,000 is going to be $168,100. And that's how we mathematically write that statement down. Now we're going to go ahead and we're going to draw a picture that represents this question. We're going to put in the very center 165,100, and then we're going to label to the left 162,100, on the right 168,100. We're going to highlight the area in between of interest. This is what the area under the curve that we're looking for. We're going to go ahead now and draw our standard normal picture. It'll look just like this, except for to have the standard deviation with our z values, our mean in the center. And now I need to go ahead and standardize this value first. And so I'm going to say z is equal to 162,100, subtract off our mean, 165,100, divided by our standard deviation, 29,500, divided by the square root of 400. Remember to use your parentheses when you punch that in your calculator. And so when you put that in your calculator, the first answer that we're going to get is going to be negative 2.03. Negative 2.03. So right here is negative 2.03. Now I need to go ahead and standardize my other value. Okay, and I'm not going to write this down. I'm going to let you verify my calculations. When I standardize my 168,100, I'm going to get a positive 2.03. So right over here, positive 2.03, and I'm going to highlight the center saying this is the area under the curve that I'm looking for, because I'm looking for the probability of this event happening. This is equal to the probability that negative 2.03 is less than z, which is less than 2.03. Okay, so this right here is going to be equal to the probability that z is less than 2.03, subtracting off the probability that z is less than 2.03. And so that is going to be equal to, I'm going to put this right down here. We're going to look up positive 2.03 to begin with. 2.03. 2.00123. So it's 9788. So it's 0.9788, and we're going to subtract off the probability that z is less than negative 2.03, negative 2.03, negative 2.00123. So it's 212. So 0.0212, and we're going to throw that in our calculator, and I'm going to find out that 0.9788 minus 0.0212 is equal to 0.9576. So, what is the probability that I randomly select 400 houses from the Northeast, and I calculate their average selling price, and I find out that their average selling price is between $162,100 and $168,100. The probability of that happening is very high at 0.9576. Now let's move on to this right here. It says, what's the probability that the mean price obtained from the sample will be lower than the population mean by 2,500 or more? By 2,500 or more. So we're going to draw a picture, and we're going to say, let's see here, what was our mean? Our mean was 165, 100. So 165, 100, subtract off 2,500. We throw that in our calculator, and we get 165, 100 minus 2,500 is equal to 162,600. And it says, what's the probability that the mean price obtained from the 400 will be lower than this right here? So we're saying, what's the probability that X bar will be less than 162,600? So we're going to draw a picture that represents that. We'll put 165,100, not 200. And then we're going to come over here, and we're going to have 162,600. And we're going to shade this area that we're interested in. And we need to standardize this. So we're going to say z is equal to 162,600. Subtract off 165,100. Divide it by our standard deviation. Our standard deviation was 29,500. So divide it by 29,500. Divide it by the square root of 400. Again, make sure you put your parentheses so that when you put this in the calculator, you are set. We'll pull up our calculator, scoot it over there just a little bit. We'll turn it on, clear it out, and we're going to start with parentheses. And I'm going to go 162,600. Subtract off 165,100. Close parentheses. Divide by, open parentheses, 29,500. Divide it by the square root. Oops, I hit the wrong thing. Can I undo that? Can I go back? Can I delete? I gotta start over. Oh, no, hold it. There we go. So square root, maybe it's this button here. It's kind of hard to see from my viewpoint here. 400. Again, remember right now I'm underneath this radical. I have to use this button right here to move my cursor out, and then I close the parentheses and I hit equals. And it's negative 1.694, so it's just going to be negative 169. So this is going to be equal to negative 1.69. And so my mirror image is going to look like this. It's going to be 0 in the center. Our standard deviation, it's going to be 1.69 units below the mean. Standard deviation is below the mean. And so this right here is the same thing. It's the probability that z is less than negative 1.69. And we can look that up in our table. 1.69. 1.69. So it's 455. So that is equal to 0.0455. So what is the probability that I'm going to randomly select 400 houses in the Northeast and find out that their average price during 1992 is $162,600 or less? The probability of that happening is 0.0455. Now, I looked at our time. We're right at an hour and 15 minutes. And so I'm not going to cover the next few slides on today's lecture. I hope that you found that this was beneficial, and I will look forward to seeing you on Thursday to discuss any questions that you may have concerning homework or today's lecture. Have a good night.